So this is a topic that when I started as a regional bridge construction engineer came upon my attention because I was handed a project with a lot of needs, and it really shook me in my shoes. But I'm going to talk about this beam end repair research that we did, some typical concrete repair procedures that we usually see out there, and then some of our concerns, and go over what the original repair project was and how we were able to capitalize on that repair project into some research. So this is some of the repairs that were done. This is a piled bent on this bridge, and typical procedure is to hammer down the concrete surface and mark the hollow sounding areas, and hopefully you have more good than bad. Sometimes the removals can get extensive, and these ones were in a lot of disrepair. Then you're going to find corroded reinforcement and supplement it. It's challenging sometimes, especially when you got stirrups that you need embedment of the leg or the hook. And then you're going to replace the concrete, and we're usually using shotcrete. That's a dry cement, sand, and aggregate mixture, wetted at the nozzle and sprayed at high velocity. And we think that high velocity, like the industry partners have told us, is really important for getting it to stick and penetrate into all those crevices. A lot of times we do this repair without load relief or any temporary support. So then it starts to, but the repair does come out looking pretty good. But then our question is, does this shotcrete really restore the strength? Or are we just covering up it and putting some lipstick on there? How durable is that repair? And how does that lack of load relief affect the repair? Another question is there an effective means if you got prestressed beam ends with all this internal stress going on? So let's attack the first question. Over time we've seen that the shotcrete a lot of times has this map cracking. This was a box girder underside that was repaired, and if I drew out the cracks here, you'd see it was a quite extensive network of cracks. I first noticed this in a repair project that we did, and then we came back a year later in a project that I mentioned earlier. It's a FRP trial, and we were required to sandblast the surface, and this is what we found: this fine network of cracks buried under the curing compound. Now, we also looked at the columns. These were repaired in 2015, and then we came back for the FRP wrap and did again find those shrinkage cracks. There's some good papers out here about how durable materials can be selected, and Iowa had a nice paper on that. Involves matching the elastic modulus, getting some good high bond strength, making sure it's thermally compatible, and then matching the compressive strength. But the caveat is you got to have a good moisture cure on that to not get the cracking. So another item we're thinking about is the lack of load relief. There's an ICRI document on this. It shows that if you're going to have forces and you're going to take out a portion of that member under the stress, those forces are going to redistribute. So that kind of lends itself to the concept that this patch isn't really participating, at least in the dead load that it's seeing, without some load relief. So if I look at this in a strut and tie type approach, you've got these internal compressive forces, and then you've got some tensile forces to keep the geometry together. Now we put that patch on there, and you want that patch to participate in any additional loading. So it's very conceivable with the high density patch and that higher compressive strength that we usually get, that you're going to develop some tensile stresses as new load comes on. And that might cause that patch to pop out, or else develop a crack along the boundary. So we think external confinement is always a good thing to add with your patches, and we're starting to move in that direction. Now, another question that we had is there really an effective means to preserve these prestressed beam ends? And that's where I'll go over this project we had. We had this bridge that I mentioned earlier. It's located in Edina. It's over a big watershed, a swamp, built by the county in 1974, and it's poorly drained wetland that you're spanning over. There's 2 road beds below this bridge from the last 100 years of construction. They kept raising it up. These are 49 spans, 60 foot each. They've got joints every other pier. So this one was handed over to MnDOT, I don't know when it transferred ownership, but had a lot of embedded chlorides from the start when we received it. The various levels of disrepair. We did repair some small beam ends, beam type repairs, and then we came in and also had some what we thought were large repairs. We didn't relieve any temporary load, and then those large actually were medium, just like the Grande at Starbucks. And that's why we ended up with some of these that resulted in a change of plan. I was called out during construction that said, well, you better take a look at this, and that web was really compromised. So what we ended up with is what we call now the large repair, right? We call it a block repair, and we had to respond quickly during the construction. What do? You start using the tools of today, and that's Google. Michigan had a repair and a report from January 6th of 2000. They had done a similar repair. So we started looking at this as a go-to, and some of the caveats there, Michigan and FHWA personnel kind of drafted this up in 1999, and you'll note they performed this on a salvage prestressed beam into lab. The beam was load tested, and they came to some conclusions that up to 1 stirrup and 12 inches of strands may be exposed without prestress or shear strength loss. Way to go, guys. 1 strand? I think you're in a lab. We should go a little further than that. But so we did some real-life repairs out here, and we had the field conditions. It was October. Our damage was well beyond Michigan, and we didn't really have a good alternative. And one of the things you'll look at with the Michigan alternative is they had this temporary support, and we thought, oh yeah, I guess that kind of makes sense. You want to lift this thing up so that you get the patch fully participating. Well, this is what happened to us. We lifted that thing up, and all the strands started ripping apart the web. We started to see a split there, and I got the call in the morning that said, hey, it's starting to breathe. I didn't really know what that meant, so I said, you got to let it down, and then we went to about a 50% dead load. So here's the sequence of repair for that box end. You'll notice on the face there's this metallizing that we had incorporated in other beams. They had come through and coated this one already. But I'm just going to walk through a nice photobiography that my inspector out there did. I will say that little puck out there is going to help us tons. That is sarcasm. Work was performed by PCI Roads by supplemental agreement. This was, as you can tell, the date was October 22nd. The repair cost for that, general beam repairs out there, we paid each beam end location cost, and that was about $700 or $800, and that included the bearing jacking cost, kind of a steal. But we did have this reconstruct that cost us $5,500 each for 2 of them in 2013, and we've since had a couple more projects where it's escalated, and we've repeated this repair. One was $12,500 it cost us, and the ones this last year were $10,000 each with a quantity of 5, shoring it extra in those instances. So we had a lot of questions. Are we getting what we think we're getting out of this? Most of the data is small-scale testing out there. We do have some industry research on shotcrete bond saying you can get to about 200 psi or around there, but to do some load calculations to say this is exactly the capacity you got, I guess we have a lot of doubts on that. And then I've gone back every year and slogged out there and kind of monitored the cracks and see if they're growing. Otherwise, we've seen some shotcrete piers destroyed and during the demo of the bridge, and we can see how if that shotcrete kind of splits off. Well, there were other issues with this bridge, not just beam ends. A lot of poor drainage in this area. And like I said, old roadbed. Some of you may have similar assets out there. These kind of ballooned on us, and it was not really part of the project. And so you start digging a hole, and then you're finding more next to you, and pretty soon you have a real problem. So we started to chase this out, and we got into some other large repairs, which were, we filled them up the best we could, but we had 43 piers out here, or 42 piers, and just a lot of piling. So the bridge was programmed to be replaced. They asked me, how long is this thing going to last after that project? And I said, well, I'd give it 7 years to 21 based on the work we did, but at that time, do you really want to put stage traffic all on one bridge when it's the most deteriorated? And so I think they took that message and they did say, let's replace this thing before it gets too long. So I sought some research when I found out this thing was going to get replaced, and I got the money to do it. And so we're going to take out 2 repaired beams that were performed and then salvage 2 unrepaired beams. And we're going to load test all 4. And I'd like to keep it simple. Just compare the strength. We're not going to try to do a load displacement on every little crack out there. Just keep it simple. So the hurdles for this was to sockhead it. The U of M laboratory can only handle 38 feet, and they had to keep it under 19 tons for their overhead gantry. So we had to take the deck off and then cast a new deck in the lab. So that was $35,000 just to get it there. I did find out after the project that other DOTs had done this, and PCI Roads had done that for them. I know in 2015 they suggested WSDOT had one. And then they said in Tennessee, U.S. Army Corps of Engineers had some also. Not the same details, but very similar. So we were able to extract these. And then we brought them into the lab and cast a 10,000 PSI narrow deck in the lab. Why 10,000? Well, we didn't want to have all the overhang brackets to do a normal width, and we salvaged the deck over the repair area and just butted up against there, and we needed to make an equivalent deck, and this was the suitable strength to ensure that we had a shear failure and not a flexural failure. Without that deck on there, you might just not get the failure you're looking for. The setup, we load tested it about 13.25 feet from the end, and the original span is 36 feet, 1.5 inches. That's what fit in their test setup, and they need to be at least 2.5 times the depth away from the end of the beam in order to get a shear failure and not just some strutting effect to the bearing. They also put some external shear stirrups on the cut end. Remember, we cut these things, they were 60 feet long, and they didn't want the failure to occur there. We started out with 50 kips initial load, and then in displacement controlled loading, loaded it up in 25 kip increments, and then we mapped the cracks. So I made a little video last night for your viewing pleasure, but sometimes the pictures work a lot better than words. Okay. Kind of like deer hunting. So we had, like I said, we had 4 tests, and I've kind of worked the 3 that I was able to go to in here. That's an unrepaired one, just a normal beam, should be the original strength. Now this one is the worst one out there. And I just threw this in there because sometimes I think it's helpful to see some things we're seeing. So the big question I had is this thing going to split off like a clamshell? Because I never trust the bond to shotcrete. And the cracks marked with E were out there. They're shrinkage cracks from the get-go. So these things, between the unrepaired and the repaired, we got to outperform in the repaired section, believe it or not, in both cases for the sets of girders. We have cores from each beam with the compressive strength in that beam. We took 2 cores per beam. The load displacement was very compatible between the repaired girder and the unrepaired. And I think you look at the comparisons, I'd say there's really no difference. The weak point is where we started to space out the stirrups. It was not in the deteriorated end, and I think it gives us some confidence going forward that there's a way to repair these without replacing the girder. I'd like to thank the Research Services for giving me this money, Ames Construction for taking it out for me, and the U of M Laboratory for putting up with me. And Eden Prairie Maintenance, boy, they had to dig all those holes to look at those piles, and they provide tons of support over the years. And then David Kogler had the photos during the construction and the headaches also. And the repair contractor was PCI Roads. So I'd like to welcome any questions you might have, and hopefully this enables you to do some cost-effective repairs out there.
How many strands were unbound or debonded, if you want to call it? And
were debonded? How many strands were debonded?
They were exposed, but they were still bonded at the end or not? I couldn't see the picture.
There was like 1 or 2 severed, and then we didn't really take off all the DLAM underneath, so I don't have an accurate accounting of that. I'm going to be completing the final report, and we'll dig into that as what the actual deteriorated condition was.
Okay, so all the deterioration were in bottom flange. I didn't see anything in the web.
For strand deterioration, mostly the bottom flange, but the concrete in the web was significantly punk concrete.
Oh.
Yeah, so we really start to question not the flexural capacity, but the shear.
No, I was questioning, what did we do shear test for? I mean, that's what I don't understand. I can follow the shear test, which is far away from the end. You're solid concrete. Am I right? On a DV, if I may, I don't want to take the
if you had a new girder, you would say that's true. Now, if you've got really deteriorated stirrups in the end, that may not be true.
So you to treat it as pre-stressed girder at the end now, or reinforced concrete?
That's a good question. Is it a reinforced beam, mild reinforced beam, or a pre-stressed? And the way we did the calculations for predicting, we just treated it as the normal pre-stressed beam, as if we still had the original capacity.
The preceding video was produced by the National Center for Pavement Preservation. More information can be found at tsp2.org. That's tsp2.org. Additional support provided by Michigan State University.